Great, so we'll get started. Hi, everybody. My name is Ian Gomez, Community Manager at H2O. Thanks for joining our Start Getting Your Feet Wet in Open Source Machine and Deep Learning webinar today. We have two great speakers for our webinar, Desmond Chan as our Senior Director of Marketing at H2O, and Amy Wang. She is our Sales Engineer and Data Scientist at H2O. Here are some logistics regarding the webinar. Please submit your questions throughout the session. You can submit your questions via the Questions tab in your console. This webinar is also being recorded. A copy of the webinar and the slides will be available after the presentation is over. Without further ado, I'll hand it over to Desmond.
Perfect. Thank you so much, Ian. Again, my name is Desmond Chan. I'm a Senior Director of Marketing here at H2O. Welcome to today's webinar. This is the first of a series of H2O webinars. And today's webinar is meant for the introductory materials. And if you are an advanced user of H2O, this may not be for you. But we will have a series of other topics in the future for this webinar series for more advanced techniques in H2O and some other use cases. And here's the rundown for today's introduction webinar. I will go into our H2O company introduction for just a few minutes. And then Amy Wang, our speaker, will go into H2O introduction and demo. She will go into details about how to install H2O and a use case for flight delay prediction. And she'll go over the use case, the data set, how to do data munging, and how to create a model in H2O. And we'll leave some time in the end for Q&A. So today we'll go over the AI platform at H2O, the core platform, which is the product on the far left of the screen. Our core platform is an in-memory distributed machine learning platform with visual intelligence. We are very much emphasizing on our visual intelligence for analytics. And in addition to our core platform, we also have Deepwater, which is our integration of all the popular deep learning frameworks, including TensorFlow, MXNet, and Caffe. And also we have Sparkling Water. Sparkling Water is our H2O integration with Spark. And last but not least, we also have Steam, which is our software for operationalizing data science in your enterprise infrastructure. And you can compare models and deploy models from within Steam. I mentioned that we are open source, and this nature of ours actually drives a lot of community adoption. As you can see from the screen, our latest statistics show that more than 9,000 organizations and more than 83,000 individuals are using H2O. And this is really tremendous for our company. We're well recognized by the press. Most recently, we are recognized as a visionary in Gartner Magic Quadrant, and also a strong performer in Forrester Wave. And in the last year, we got 46 press mentions, on popular press such as Wall Street Journal and TechCrunch, and so on. And out of the Fortune 500 companies, 169 of them really love us. They are using us on a regular basis. And you can see that banks, telecom companies, and health insurance companies are using us as well. I want to give you some anecdotes on why we're chosen for Gartner MQ, the Magic Quadrant, and also Forrester Wave. For example, in Gartner Magic Quadrant, you can see that we have very high regard from our customers. And Gartner also thinks that we are especially suited to IoT, edge, and device scenarios. And for Forrester, again, they recognize that we have significant adoption by the large enterprises. And when big data was just on the rise, H2O was the only or the best known for developing open source cluster distributed machine learning algorithms at that time, and no one else had them. And also Forbes recognized H2O as one of the top 10 AI technologies amongst other competitors such as NVIDIA, well, not competitors, but people in the companies in the ecosystem such as NVIDIA, Microsoft, Google, and so on. And if you're interested, you can actually go on our website, www.h2o.ai, to find more video talks from our customers, from different verticals such as auto insurance, commercial insurance, financial services, and retail, and so on. So there are many of those videos on our website. And if you are so inclined to know about our use cases, please do so. And again, just as a reminder, we will have more webinars in the future about use cases in different verticals. That said, I want to hand over to our speaker, Amy Wang, and she will go into the technical details.
Hi guys, this is Amy from H2O. As mentioned before, I'm a sales engineer at H2O, so my job primarily have been about installing H2O on big data environments, as well as working through data science problems with customers. So, please send in questions as I talk, and we'll try to see how many we can get to. So first, we're going to go over basically the overview of what H2O is, some of the features available out of the box with H2O core, and then I'll go into a airlines demo showing you some of the features on a multi-noded H2O cluster. So what H2O is an open source in-memory computation engine, essentially. The entire platform is built to fit into a jar file that you can launch as a JVM, and you can launch many JVMs so that you have distributed platform, and in each individual node you have computation also parallelized. So on top of that platform, we basically built a few machine learning algorithms, including GLM, random forest, GBM. Deep learning is one of the open source neural network algorithms out there that's free and open, easy to use from the H2O platform. So please try that. And on top of that, we have a API built in, the REST API, where we built in R and Python client interfaces. So instead of having to write Java code to core H2O, which is what H2O is written in, you can write R and Python code communicating what you want to do to the H2O cluster. And I'll show you the R client in the demo later. And one of the benefits of using H2O in particular is that you're able to use all your data. As much as you can scale out the resources that you have on your environment, you can fit more and more data into that environment. So it really scales as your data grows, or you have more use cases. It's faster to iterate through all those different models, all the different techniques, and get at the best model with the best predictions and the fastest predictions as well in production. So these are a few of the algorithms I just mentioned a little bit, but basically supervised learning is essentially if you know the answers to your questions and you know the target to which you want to predict, be that a binary, is a flight delayed or not, or a regression, how many flights should we have in one day to meet demand. So these are the type of questions that you can sort of answer with models like GLM. Naive Bayes is used for binary text classification. For tree-based models, we have distributed random forest as well as gradient boosting machine. And for neural network, as I mentioned before, we have deep learning. Then for the unsupervised learning methods, this is typically clustering, doing dimensionality reduction on a data set, or detecting anomalies. These things are things that you don't have sort of a targeted or response column to predict for. You just sort of want to gain insight on the overall data set. And for clustering, we have k-means, or for dimensionality reduction, we have PCA, principal component analysis. We also have something that's not really available in any other platform called generalized low-rank models, or GLRM for short. And this is sort of a general convex optimization method that could be used to do clustering and dimensionality reduction. You can use architects in GLRM to partition your data set into something that's similar to the k-means method. And you can also use it to do dimensionality reduction to reduce the dimensions of your data set. And then finally, we have autoencoders in deep learning, which is a simple one-layer network that basically tries to replicate the data onto itself. It's a nonlinear transformation back on itself, and it could be used to do anomaly detection. So just an architecture deck to look over our stack. We have, we're able to sit on top of any sort of commodity hardware, be it Hadoop or any regular machines. We launch as JVMs, but if you launch on top of Hadoop, for example, we have built-in readers to read in data from HDFS. If you launch on EC2 instances or you plug it into S3, we can read in data from S3 buckets. We also have a JDBC connector that will allow you to query simple SQL tables into H2O, into in-memory H2O framework. And this is what you'll see that is the core of H2O. We have an in-memory framework. Once you read data into H2O, everything sits completely inside of H2O. All the work is done inside H2O. We have a MapReduce framework that I mentioned before. That's not Hadoop's MapReduce, but our own flavor of MapReduce that's written in Java. That's extremely fast. When you read in data, the data itself is also columnar compressed, so that it's expressed in a way that actually saves quite a lot of space in terms of memory in the cluster. So you have more memory to do your work on. And it's our special format of expanding or contracting those data formats. So, and then once you have the data in H2O, you can do a variety of things: feature engineering, munging the data. You can do simple things like doing unary or binary functionalities on a column in a H2O frame, or you can do feature engineering. You can apply something like deep learning with deep features, which will extract features out of the neural network. So there's quite a lot of different methods that you can use in H2O. And then finally, the traditional machine learning algorithms you can build on top of the data that you read in. And all of this you can do, again, as I mentioned before, via the REST API. And we built the R package really early on in H2O's infancy, so that our users, which are our primary audience, the data scientists, could communicate without having to write Java code, using our syntax that they're familiar with to give commands to H2O to execute. And I'll show you a diagram of that in a little bit. And of course, we wrote Python about a year or two ago into that stack as well. So we have a Python module that you can actually just pip install, which is really easy to do. And then, of course, we have H2O Flow, which is our web-based UI that you can actually, it comes out of the box with H2O, and you can point and click through and manipulate H2O in a non-programmatic fashion. And I'll show you a little bit of that as well. And then, of course, Java and Scala, which is native languages that we plug into. And so while you're writing these code on the front end, what's outputting in the back end is Java code. It's a plain old Java object, which is our scoring engine. And this scoring engine can be taken completely outside of H2O into any production environment that can basically read Java code, or we can write a C interpreter on top of that as well. And then we can get into that in a separate webinar. If you have questions, we can also go into that a little more. So as an example of how the REST API works, if you were an R user trying to import data set into H2O, just to look at the data, you would do a simple R function call. That's H2O.import file. So instead of doing read.csv, you would do H2O.import file, and again, just supply the path of the data to the function call. And what happens is this R function call is carried over the HTTP network via the REST API to one of the H2O nodes that it's connected to. And the H2O node will parse that information as a command to import data from HDFS with the path that you've supplied. And it will tell all the other nodes on the H2O cluster to do the same. And all the clusters simultaneously hits HDFS to request for the same piece of data. And as we're reading in data, what we're doing is that we're reading in the data as chunks. So chunks of data is being read in one at a time, in parallel, but chunks of data is sort of being read into each of the nodes until there are no more chunks to share across the nodes, essentially. And once we've imported that data set as a parallel and distributed, data frame, what's returned to the R user is not the entire frame. We only return a summary of that data set that's a distributed frame. We return a summary of that to an R user. So they can look at it like it's a regular data frame, truncate it a little bit, but they understand what the data set look like and feel like, and they can always query the entire data set, which is available in the H2O cluster. So these are the functionalities that you would expect to have parity of in H2O and R, and this works for Python as well. So instead of using read.csv in R, you would use H2O.import file in H2O and R. Instead of using summary, we actually overload the summary method, but things like cbind and rbind on a data frame, we've prepended H2O dot, so you have to do H2O.cbind or H2O.rbind on an H2O frame. Unary and binary operations are also overloaded, so we'll detect whether or not it's a data frame or a H2O frame and use the appropriate method. And then for the algorithms, instead of using GLM, GLIMnet, you have H2O.glm. Instead of using random forest, you have H2O.random forest. So, analogous to a lot of the algorithms that are currently available in base R. Again, a lot of the functionalities are just prepended with H2O dot. So predict, H2O.predict. There are functions that you would have in other R packages that are not supported in H2O. There are ways to bring back sub-snippets of the data set that can fit into R, back into R, and use whatever R packages you want. And I can show you how to move data between standard R and H2O and R. But for the most part, you want to do as much of your big data work in syntax that's built for H2O and R. And just before we get started, if you guys are interested during this call or after the call, it's really easy to install in R and Python because we submitted the package to CRAN and with PyPy. So what you can do is just in R, you can install that packages, H2O, and if you're using Python, for example, you can do a pip install of H2O. If you have Conda, there is a Conda install H2O as well, and there's also a web page with more instructions on how you can install on a multi-node situation rather than just on your desktop as a trial. So I'm going to go into my demo. I'm going to exit my presentation here, and I'm going to pull up my R session. And for this particular demo, I'm going to use an airlines data set based out of Chicago. And I'm going to use Chicago weather. So we wanted to predict for weather-based airline delays. So whether or not a flight will be delayed based on the weather. So we don't care about whether or not an airline, a flight might be delayed because of, let's say, there was a logistics issue or there was a bad global event. This is strictly dependent on weather so that you sort of narrow down the scope of your problem to something that's solvable. So we'll start with that. And then we start by loading the H2O library. And I have an H2O cluster up that's only 2 nodes, 10 gigabytes on each one, but I can connect to the remote H2O cluster from my local R session. So right here, when I click connect, you can see that it's not a single noded H2O instance. You can see that's 2 nodes, about 20 gigabytes across the the entire cluster, and about 64 cores that is available for the H2O instance to use, right? So it's a fairly hefty cluster. And what I'm going to do here is I've specified some HDFS paths, and I'm just going to define them, and then I'm going to read it in with H2O.import file. So while that's importing, it's going to import relatively quickly. I think it will take about 2 seconds here. I'm going to bring you over to Flow, which is our web-based UI, so that I can show you, even though we're doing work on my local machine and you're looking at it through R, there's different interfaces because it is through the REST API. There are different interfaces that you can hit. So I just imported a data set. I can actually hit get frames in the web UI, and then you can see the 2 frames that I just imported. This flights data set on disk is about 1 gigabyte, 1.2 gigabytes. Read into memory, we've compressed it down to about 373 megabytes. You can see it's about 12 million rows by 31 columns, and the weather data set is smaller, but we would join the 2 to essentially grow the original data set to have more features. And you can click on the individual frames itself, and the columns to see the distributions of the columns, as well as you can convert some of the numeric values to enumerators or factors and vice versa. And there's ways to build models straight from Flow instead of R, so you can hit build model here, or you can split the data set right from the web UI. But today we're going to go through the R interface. So the same way we can describe the data in Flow, you can also hit H2O.describe, and you can look at the min-max mean of that data set, the cardinality of enumerator columns, how many missing values are there in that particular column, how many of them are zeros. That could affect which algorithm you choose, which parameter for each of the algorithms that you choose. There's also some simple plotting functions like histogram, so we can bin some of the information from, let's say, the year column. So now you have all the flights per year that's in the data set. And you can see a bit of a gap in the middle here because we took out one year. We can do some other plotting functions where I'm munging an H2O frame. This thing is a huge H2O frame. That is truncated. You see only the first 6 rows by all the columns, but it looks like it and feels like a data frame. It's just, it's an H2O frame when you see it's truncated like this. And I'm just going to do some simple work to define whether or not a flight is delayed based on weather. I'm going to do a group by, which is a really fast H2O like ddply-like function that allows you to do aggregations. And you can see that the aggregation across 12 million rows with 20 different subsets took about 1 second to do. And what's returned is a relatively small H2O frame. It's 20 rows by 4 columns. And this is what I mentioned before. Something like this that you finish aggregating upon, you can bring back into R. So you can do an as.data frame to translate this H2O frame back into an R data frame. So I'm just going to do that. And then from there, I can do whatever I want. That's a typical R command, right? So I'm plotting the results of that because I can translate it. And you can see the blue line here is the number of total flights. The red lines are the total number of delays. And all the way at the end here is a little purple bar that's specify weather-based delays. So you can see a lot of the other years back didn't even track whether a flight was delayed based on weather. So we're just going to subset that, and we're only going to take the ones from 2003 to 2008, which actually have weather-based delays. And we're going to take everything in the blue bar, everything in the purple bar, and try to predict for the little purple bar, essentially. So here we're doing some simple filters. If you're an R user, you'll understand this syntax. It's just, you have a frame, you want to filter by a column and the value that you want to filter by, and you reassign it back to the original variable. So the syntax itself, if this was a data frame, would be exactly the same for the same type of operation that you want to do. So it's really easy to get started with just munging the data set. And then we have an overview of after we filter it, we have about 82,000 weather-based delays out of 2 million, and we want to predict for that and get a decent ROC curve and AUC value. You can see I have a few parameter creation functions here. This is basically taking an H2O frame. I'm going to do a modulo mod, and then we can create a new time variable that we append back to original flights hex frame. And so the flights hex frame, which originally had about 31 columns, you can see I've appended 3 new columns on here, here, and then finally travel time here. So, and then finally, we're going to build our machine learning model. So I'm going to set my Y predictor and my X predictor, my predictor variables, and then I'm going to predict for is arrival delayed based on the year, the month, the day of the month, the day of the week, which carrier, United versus Delta versus JetBlue, where you're flying from, which in our case is all the flights are flying to Chicago, so we didn't put the destination, right? We have the travel time, how long you spend in the air, or the distance of that flight, essentially. We'll do a test train split so that we can verify, we didn't define this, we can verify the error on the training set is representative of new data coming in on the validation set. And then we're just going to call H2O.glm right here with the X, Y variables, the training set, the validation set. This is a binary classification problem, so the family is binomial. We have some regularization in here, as well as turning on lambda search to search through different lambda values for that regularization path. While I'm doing this, let me pull up Flow again, and I'm going to pull up the water meter. And the water meter is basically, you see each box is one machine on the H2O cluster. And the individual blue line is a core on that machine. So what you should see when I hit execute to build the GLM model, you should see both boxes spiking up in green, meaning that the cores are busy all at the same time and reducing at the same time. And so you should see that on the side here. So we're going to build a GLM model, and then we're going to build a GBM model with about 50 trees with the same parameters. And this is an easy way to, let's say, try all the different algorithms with different parameters and see which one works best for your data set, right? So it depends on how sparse your data set is, categoricals versus numerics. One algorithm might work better than another. An easy way to find out the behavior of the algorithms with the data set is just simply to try it. And with H2O, you can basically try GLM, GBM, deep learning, random forest, all in matters of seconds and see generally out of the box which one does better. So I'm going to report back the AUC on the GLM and GBM model, and you can see that GLM didn't do as well as GBM. There's no overfitting in GBM's case either, because you can see that the AUC value on the training set and the validation set is fairly similar. It's a little lower, but we expect that out of the validation set. And we want to know if we can improve upon it. This is just a regular data set without weather data, right? So if we merge that data, the original data with weather information, whether or not the new information can improve this original AUC value. So here we have H2O.merge. This is written by Matt Dowell, who written data.table, and it's supposed to be a very fast, it is a very fast merge that you can use a multi-node or a single node. And we're just going to merge by the time of the flight, so day, month, year, and we can look at the merge data, and you can see instead of the original 32 columns or the weather data set, which is 27 columns, it's going to be the combination of the two with 48 columns with all the original 2.2 million flights that are in our original training set. And of course, you can view it from Flow as well. You can see the new frames that you created, as well as, let's see, as well as the models that you built. And I'll show you in a little bit after I built, I built the weather-based GLM and GBM model. So I'm going to split the data again. This time it's the new frame that we created we're gonna again define our response variable to be arrival delay, but the predictor variables will have new incoming data from weather hex essentially. So you can see the new feature set is much larger than the original. There's about 31 predictors. And then we're going to build GLM, a GLM model, and a GBM model here. And again, you can see the core sort of working away. And funny enough, while this is working, I can go into H2O and grab the model that is actually currently being built. So GLM is being built right here. It hasn't finished the full regularization path, so you don't see it yet, but you can already see in this current iteration, what is the coefficient of that model? And if you like what you see, you can also actually stop the model build in the middle, and the model is ready for you to take into production with Java code that's also created on the fly. So it's already built the GLM model, and I can refresh it, and you should have the ROC curve. You should have the ROC curve on the training set, which is, you can already see it's better than the 0.7 that we got before. Is now 0.8 with the new features. Again, on the validation set, you see a similar AUC value, and going down some more, you have the magnitude, the standardized coefficient magnitudes for that model. And there's a few more metrics that you can play around with, and again, the POJO is available for you. And if you want to see really quickly, I can do get models again, and you can look at the GBM model that we just finished building as well. And it looks slightly different because it's going to have the ROC curves again, but you can see the AUC value in this particular case is much higher than the original GBM model as well. But you also get a scoring history, which is particularly useful if you're worried about things like overfitting on your data set. You can see how well a model did on the training set and the validation set over the number of trees. So let's say you built 1,000 trees, but you notice that it starts to overfit near like 50 trees. You can actually prune that model early and take that model out instead of just letting it continue building and start to overfit essentially. So it's a good tool to combat or diagnose overfitting issues in tree-based models like GBM or deep learning, which also could have an overfitting issue as well. So I'm going to report back the AUC in a new table so we can look at it and compare the AUC tables. And you can see here in the original data set, the GLM has 0.74, now that's 0.85. GBM originally had 0.84, now it's 0.9. 91 almost. So you can see that it's done significantly better to add more features in. And particularly as a data scientist who needs to translate these models into business value, you want to be able to interpret the model. So, you kind of can say that the AUC represent how accurate this model is in general. So between the value of 0 and 1, it's sort of like 70%, 80%, 85 to 90, which looks good. But interpreting the model itself is a little more difficult, and we can do that easily with, let's say, a GLM model, which if we go into a GLM model, you see the coefficients for each of the variables that we use. If you see right here, we have, it's sorted by most important or the most effective to the least. So you can see a categorical column with rain, with the values rain, hail, and thunderstorm would obviously have a positive coefficient that's relatively high in this data set, which means as you have this variable, if it's raining and hailing and thunderstorming, you can expect a weather-based delay on your flight. And these are relatively easy to interpret. But something like a GBM model, for example, let's pull a GBM model. What you have is variable importance. So you can kind of see how important each of the variables were in terms of improving the accuracy on the model. So you can see that origin was split by on multiple times, more frequently than maybe other variables, and each time it was split by origin point where you're flying from, you get a decrease in your loss function, which is improvement on your model. Another way to interpret it in H2O is we have something called partial dependence plots. So you can do grab the variable importance and look at the most important variables, and then choose a few columns to calculate partial dependence plots. So here I picked, visibility by miles, precipitation in inches, the max temperature, and the max or the mean wind speed in miles per hour. So if I calculate the partial dependence plot right here, and you can see all the jobs are happening in Flow as well. Let me see if I can grab that here. You can see the partial dependence plot being calculated here. It's still running, and you can refresh it as it goes along. And this typically for 4 features, I think it will take about 20 to 30 seconds because it's scoring repeatedly over the same data set with different values for each of the columns. So it's a little more computationally intensive. But once we finish that, what you have are plots that you can view. So for example, we have the mean response versus the visibility by mile. So as you have less and less visibility in front of the plane, or you should have a if you have more, this is increasing here. If your visibility increases, the visibility in front of you increases, you should see that the response for arrival delay will decrease. So you're less likely to be delayed if you can see what's in front of you. You can see that if it's raining more and more, you're going to be more likely to have weather-based delays. And this is another way to interpret, traditionally not easy to interpret machine learning models. And this is sort of an area that we're working really heavily to try to improve. So you can see, you can interpret things like deep learning models that have really complicated networks. You can explain a GBM model and the features going into a GBM model a little bit, even though this is going to be 50 trees or 100 trees, shallow trees, that is usually not easy to interpret. And with that, I think I'm done with my RM Flow demo. I don't know if, yeah, okay, yeah.
Awesome. So we'll go ahead and transition into Q&A. We have some great questions in the questions window. Let me go through them real fast. So the first one is, what is your business model? Great question.
Great question. So Ian, let me take that. So our business model, as you know, we are an open source company, and we offer enterprise support. And the measurement of usage is based on the terabytes of data that you have. And also we offer different types of SLAs according to the tiers of support that you get. If you have any more questions about our enterprise support, please just reach out to our sales. The email address is sales@h2o.ai.
Awesome. Thanks, Desmond. So here's another question. What does your roadmap look like?
Yes. So again, let me take that. There are many exciting things going on. Just to give you a preview, in the near future, we will have more announcements about our GPU enablement, meaning the machine learning algorithms being very integrated with GPU and run accurately and on a speedy fashion on GPUs. And also for Steam, we are working on securing the Hadoop infrastructure for Steam users. So that is another thing that you might want to look out for. And going forward, our ultimate vision is all about accuracy, speed, and model interpretability. You must have seen our blog on model interpretability by our co-worker Patrick Hall and Wen Fan, and also our CEO Sri Empati. So if you're interested in model interpretability, that is also one direction that we're going in. So hopefully that gives you a preview of our roadmap. And Ian, go with the next question, please.
Awesome. Thank you so much, Desmond. So let me filter through these. I have some good ones. Good one. Do you hold actual face-to-face meetups? So we do. We are growing our meetup communities throughout the world. I know that I posted this in our various cities in the US. We are looking for community champions in those cities, so feel free to directly email me at ian@h2oai if you're from one of those cities that we posted this kind of meetup webinar at. Thank you for that question. Next one. All right, so does H2O have support for SVM?
Yeah, so H2O out of the box have the core algorithms we mentioned before, but SVM is not one of the algorithms out of the box in H2O, but it is with Spark. So you can download H2O's sparkling water installation, and you'll be able to basically use SVM in sparkling water.
Awesome. Next question. What is the open source licensing of what was demonstrated?
It's Apache. So it's just Apache v2 license.
Perfect.
Tom, do you have anything to add to that?
Nope, Apache v2.
Yeah, that's.
Okay. Let's go on to our next one. Do you have support for CNNs, convolutional neural networks?
So again, H2O deep learning is just a feed-forward neural network, but there is deep water that will be that is being currently worked on that will allow you to use other deep learning or neural network platforms, which will include convolutional neural networks. So you can use MXNet, for example. Sorry.
MXNet, TensorFlow.
Yes.
There were a number of questions about that and also about GPU support in general. And so just keep an eye out for a future webinar, which will get into that in more detail. And you can check out the projects that are being worked on GitHub. So the Deep Water project is also open source. It's on GitHub. You could go take a look at it. There's an Amazon machine image that you can use, which is probably the easiest way to consume it today. And so I would, if anybody's interested in that, I'd encourage you to go look at that as our way of delivering that to you.
Great. So we'll get to another question. We have some time.
There was one here about a particular regression model that I'd never heard of, LOESS. I apologize, I don't know what that is. And so I guess that means we don't support it, most likely.
Yes.
Yeah.
But we can probably look.
Yeah, so that would be something that we'd have to look into. So the person that asked about that, if that's really interesting to you, then write to us and we can follow up on that.
So I have another question. Is there functionality for running streaming predictions with live data?
That's a good question. So yes, you can take the H2O models and in the Pojo or the Mojo form and actually embed them in lots of different environments. And so an example of a streaming environment would be either Spark streaming or Storm, a Storm Bolt. And so you can take H2O models and very, very nicely embed them into environments like that, because the final Pojo or Mojo model has very little software stack. It's an extremely, extremely thin stack. It does not require the full H2O to be running to make predictions in a streaming environment. So those are great deployment options, especially for real-time use cases.
Awesome. Thanks, Tom. Let's go through some more questions here.
Yeah. Can H2O get data from MySQL? Amy, you want to take that?
Yeah, so there is a JDBC connector. So if you take the MySQL driver and launch H2O with that driver, you should be able in R, I didn't demonstrate this, but there is a function call in R and Python H2O.import table or H2O.import SQL table that will allow you to basically query a table out of a database and into H2O as an H2O frame in memory.
Okay, and there were a couple of questions here about Azure. Do you have an Azure image? And then another one is, this one's interesting, is H2O like MS Azure but with clusters? Do you want to say a few words about Azure, Desmond?
Yeah, so with Azure, we do have a partnership with them, and we do have our H2O deployed in a container on Azure.
Yeah, in the Azure cloud.
Yes.
So H2O is just a Java process. It can really run anywhere. It can run on all of the different cloud frameworks. It can run on EC2. It can run on Azure. It can run, on all of them. And so it is possible to run there. And an image or a convenient way of doing that is actually in the works and might even be available. We'd have to check on that if it's available for everybody today. But if it's not available today, it's one of those things that's actually under development. So keep tuned for that. How to import R libraries into H2O? That's an interesting question. So what is probably the right way to answer that is to say that what we've done with H2O is we've taken a set of core algorithms and rewrite them in Java to be parallel and distributed. So what we don't do is take all of the thousands of CRAN packages and magically run them in H2O in a parallel and distributed way. We've taken very specific ones like GLM and random forest and gradient boosting and decided to re-implement those in Java in a scalable way and focus on those. But what's nice is you can also move data back and forth between your desktop environment as well as the H2O cluster environment, and so you can use those different packages side by side. You can actually use the R packages that you're used to using side by side with the H2O package. It's only the H2O package's actual capabilities, though, that will be parallel and distributed on the H2O cluster.
And just to add to that, the unary and binary functionalities are there. So if you have something simple that you want to implement, you can actually write R user-defined functions using H2O on the back end. You just have to be sort of clever about it, but it is doable, and you can sort of re-implement a lot of functionalities out there in R.
Here's a fun question. What does Mojo stand for?
Oh, yeah, that's
and so my understanding is that mostly it's just that it sounds cool. I think it actually does stand for Model Object Optimized. Yeah. Is that right?
Model Object Java. Yeah, I don't know where the Java sticks in there. I think
it's Model Object Optimized.
Yeah.
But honestly, mostly it's just because it sounded cool. Yeah. The difference between Pojos and Mojos is probably worth spending a moment on, just because we want to differentiate between the two. The Pojos are generated code representations of models, and Mojos are generated data representations of models. And so you can look at the Pojo and you can look at, for example, a tree model, like a gradient boosted tree model, and look at the Pojo for that, and it's quite easy to see the different decisions being made because it's literally if then else code that's generated for the implementation of the model. With the Mojo, instead of generating code for the model, we generate a data representation of the model, and then there's a little interpreter that knows how to walk the representation and take a new row of data and make a prediction for it. And so, the two different modeling implementations, Pojo and Mojo, have different trade-offs and different kind of strengths and weaknesses, and it just sort of depends on your environment. But they're both very good for real-time use cases. They're both excellent for that.
And then there's another question about. Oh.
Sure. The other question is, do you have use cases for Mojos to do anomaly detection and data quality management?
So, just more questions about Mojos, but, we have the Mojo right now for all the algorithms in particular. I don't know if we can build in the anomaly detection, the autoencoders from deep learning into Mojo as well.
Yeah, I don't know if it's there actually today. We'd have to look.
Yeah.
It's definitely in the Pojo though.
Yes.
So if you wanted to use that, then that's definitely available. And the way that the intent is that eventually we'll put everything into Mojo. We just sort of do it according to who's asking for what and when. So we absolutely intend to make everything available in the Mojo form factor.
It's just that we work on these demands based on the frequency of the requests as well as who make these requests. So whether a customer needs it and it's a blocker to go into production versus it's an open source request from the community, that sort of,
Yeah, so we definitely, the short answer though is we will absolutely have that. That's absolutely in the plan. Here's a question. Do you have support for the Lua programming language? And we do not. That's not something that we have today. We've got R, we've got Python, we've got Java, Scala, and those are kind of the primary set of languages. Are we planning to have a physical meetup in location X? So is there maybe well, so there were a few of these.
Where's location X?
Yeah, there were a few of these, and so maybe the right way to to answer that is to say on our website there's an events page, and that has a list of where the upcoming meetups are. And I think Ian might have touched on that, and I'm just reiterating. Let's see. Could you point to some resources for learning about H2O, learning further about H2O? And the best resource to start at is the H2O documentation page. And actually, it might even be a good thing to bring up and to show everybody. So at the docs.h2o.ai page, you will see an overview of all of the documentation, and then you can drill into various parts depending on what you're interested in. So you can zoom in on the algos, you can zoom in on the H2O user guide. That's actually kind of the quote-unquote main H2O documentation, the H2O user guide. And we've been putting in a lot of effort to try to make this more and more comprehensive over time. The most recent addition to this has been an extremely detailed parameter documentation for gradient boosting, for example. So you can find a very, very thorough parameter by parameter example of for gradient boosting, where there's a code snippet for each parameter, and as well as a description of what it does. So I would say this is a great resource. And if we just back up to the main page again, there are other high-level topics, like there's a grouping by language, grouping by tutorials. Many of the conference presentations and meetup videos are available here under the presentations link. And for developers, there's developer documentation, and then kind of architecture and security and productionizing recipes for enterprise folks. So this is definitely a very the place that I would start if you're looking for H2O documentation all in one place. It's docs.h2o.ai.
And on that note, I think we got a question about whether how it is different to run H2O online or on your desktop. So on your desktop, you have your laptop resources, the amount of memory and CPU that's sort of limited to what a laptop can bring. Online or on a Hadoop cluster, you have usually more resources. You have more nodes, more CPUs. You have someone to do security around your data file system. You have people to manage those resources, things like Yarn. So typically we try to, plug into wherever you have a big data environment. But to get started, if I didn't mention it before, there is also an H2O.ai/download page that you can hit. That, if you go into the latest stable release, if you get started, you might want to download just a jar file, or you want to just install an R and Python on your desktop to try the functionalities. But eventually, if you want to install on Hadoop, for instance, there's sort of a different way to install, but the functionalities will essentially be the same.
Okay, and then here's a question: does H2O have support for neural networks? So I'm sure that Amy mentioned that, and yes, there is a deep learning inside the core H2O. So core H2O has a feed-forward neural network framework with backpropagation, and it's a CPU-only framework. So that's going to take advantage if you've got a distributed Hadoop environment, for example. You can run deep learning in just regular core H2O on your CPUs in your cluster. And from the standpoint of our kind of next generation deep learning and kind of taking advantage of GPUs and doing things like CNNs, for example, that's in deep water. So you can go check that out, and we'll put that in I would say that belongs in its own webinar as a future topic, because that's a very good topic to cover. I think we're getting close to running out of time here.
Awesome. So I guess that will wrap up our webinar today. So I know a lot of you have asked if there's going to be the slides and recording available. So yes, they will be. They'll be on YouTube in about 24 hours, and the slides will be posted to the respective meetup groups as well. And we'll follow up with a survey just to get your feedback on our webinar and future topics. Special thanks to Amy and Desmond for presenting today. If we weren't able to answer your question, and Tom, if we weren't able to answer your question, please ask on stackoverflow.com. And if you haven't tried out H2O yet, feel free to download it on our website on H2O.ai. Thanks again, everybody. Have a good day.